All right, we got Unit 4 Progress Check MCQ Part A. Let's go ahead and get into question 1. So what you see here is going to be a block on a ramp, and you have a whole paragraph underneath describing what's happening. But essentially what's happening is that this block is being pushed at an initial velocity of whatever it is. It's going to be the same for all trials. And then this block is going to travel up the ramp to a certain point B. So it's going to move up to a certain point B, and it's going to reach a certain height. So that's going to be h, which is the other variable on the table. So we have two variables. It's going to be theta, which is the angle of the ramp, and the height. So how does the angle of the ramp affect the height at which the block travels up the ramp? So whenever I want to look at the question, I'm going to move down here, going down. So a student must determine the effect of friction on the mechanical energy of a small block as it slides up a ramp. The block is launched with an initial speed of v0 from point A, slides up the ramp, and then it gets to point B. At point B, the block comes to rest. So at B, the block comes to rest. The student performs 3 trials. Okay, question is that we need to determine the initial total mechanical energy of the block or system. So this is where we use our conservation of energy equations. So if we want to use our conservation of energy equations, we have to do E initial equals E final. We know that initially the block will be pushed, and it's pushed with a certain velocity, so it's going to have kinetic energy. It doesn't have potential because there is a height of 0 at the ground. So if the block is away from a point at 0, like it is in B, that means it will have potential energy. So whenever it's at the very top of the ramp, it will have potential energy, which is U. And then that's just going to be all we have for those energies. So then K will equal U. Kinetic energy will equal potential energy. And then if we want to know the initial total mechanical energy, we're going to look at K. We don't look at U because that's our final total mechanical energy, and therefore our answer shall be D. Let's go on to question number 2. So we want to go to question number 2. Consider the trial with the 45-degree ramp. Suppose that the block is launched up the ramp such that it comes to a point at rest and then travels down the ramp. So I like to draw my little block. So my block is going to go up the ramp, and then it's going to go down the ramp, and then it's going to come to rest. So, well, it's not going to come to rest. So we have 2 points where K naught, which is our initial kinetic energy, and then Ka, which is where it's going to be reaching the point A at the bottom again. So Ka is going to be whenever the block gets back down the ramp. K naught or K0 is going to be the initial push. So if we initially push this block with a certain velocity, and we know that kinetic energy relies on 1/2 mv squared, we know that whenever it goes up the ramp, all that kinetic energy turns into potential. When it goes back down, that potential energy gets transferred into kinetic energy. So theoretically, if there was no friction on this ramp, there should be the same amount of kinetic energy going down. However, this block is going to be frictionless. I mean, it's friction full. So because there's friction on here, that means Ka, you will lose that mechanical energy to thermal energy. So because there's friction, all that mechanical energy will be lost, causing the block to slow down. Whenever the block slows down, we have less kinetic energy going down, and therefore our answer is going to be B. So because the force of friction removes the mechanical energy from the block earth ramp system on its way up and down the ramp. Let's go on to the next question. Consider the trial in which the ramp is at a 20 degrees angle with the horizontal. The surface of the ramp has been replaced with, it's basically frictionless. If the mass of the block is doubled and the initial launch speed is doubled, so we're going to say that mass of block is doubled. So m becomes 2m, and then the initial launch speed, that's going to be v, it becomes 2v. It's doubled. How could the student predict the new vertical of the block at point B? So if we wanted to find the vertical height of point B, right here, I already know that I can use my conservation of energy equations. So if I use my conservation of energy equations, I have 1/2 mv squared equals mgh. Those are my equations. I solve for h right over here to find height, but it wants us to double the mass, so 2m, and then double velocity, so 2v squared. Okay, so we don't really need to go that far, but if we ever did, this is what we have to do to find height, and then we would solve for height. So it's going to be B. Next question. Let's go on to number 4. So number 4, we have our system problems. So a block of mass m is on a surface. The spring, you can ignore the mass of the spring. The spring is attached to the wall. There's no friction, so neglect friction, neglect mass of the spring. The block is pulled to a position and it's stretched from equilibrium. So say this is going to be where equilibrium is. And then it's stretched, so it's going to be stretched. Okay, so it's going to be stretched. It's released from rest. So which of the following system is classified as a closed system? So let's define what a closed system is. So a closed system is going to be a system in which there are no external forces. So there are no forces acting on the outside of these. Here is my pseudo block here. We have the system containing the block, the system containing the spring and the earth. So I'm going to write earth. The system containing the block and the spring. The system containing block, spring, and earth. So our question is, which one of these systems have no external forces? And of course the answer is D, because we already know. Let's see why A, B, and C are not. So one thing that you can always rely on is Earth. Earth provides gravitational force. In the case of the red and blue systems, so the block and the spring, or just the block, both of these systems have an external force of gravity. So because there is gravity acting on these objects, therefore, we can just mark out A and C. Letter B, we got spring and earth. This time, it includes force of gravity, but it only includes the spring. It does not include the block. So the thing about there not being the block is that the block should provide a force that is acting on the spring. So because the spring is acting on the block in return acts on the spring. That's Newton's third law. So whenever you apply that, you can know that there is an external force. Let's move on to the next question. So number 5, we got a graph, a nice little graph here. We got total mechanical energy. I know that because there is a change in total mechanical energy, that automatically tells me that there's going to be an open system involved. So open system would mean that there are external forces, and or mechanical energy gets turned into non-mechanical energy. And just a reminder, non-mechanical energy would be things like thermal energy, which is due to friction, or air resistance, which causes you to change that mechanical energy to things like sound or sound energy. Okay, so our question: the total mechanical energy of a system as a function of time, which of the following statements is true? It's going to be B. The system should be classified as an open system because mechanical energy can be added and removed from the system. Letter A says the exact opposite. So that even though energy was gained and lost, and in the end we return back to our regular total mechanical energy, it doesn't matter. Energy was removed. Letter C, the system should be classified as an open system because the curve on the graph is symmetrical. That does not make sense. Letter D, the system should be classified as a closed system because the system's total mechanical energy does not change from T0 to T10. That is not true. So it's going to be B. Number 6, in which of the following systems does the total mechanical energy of the system remain constant? So based off the last question, sorry in the background, my cat is using his litter box. Ew. So if we want the total mechanical energy of the system to remain constant, then it needs to be a closed system. So remember, closed system, all your mechanical energy stays mechanical energy. So mechanical energy to mechanical energy. In an open system, some of that mechanical energy might be transferred into friction, into non-mechanical energy due to friction. So we already know open system, we can just cross that out. Okay? If we want mechanical energy to remain constant, then it needs to be a closed system. Let's look at the closed system containing the planet. Well, that's not really a closed system because, as you can see, the planet's over here, but it's within a distance with the star. So the star is going to be providing a gravitational force, and so is the planet. Okay? So they're both having equal and opposite gravitational forces between each other, which allows them to orbit each other. Let's go on to the next question. So number 7. All right, we got number 7 here. A 5 kilogram object is released from rest. So here's my picture. It weighs 5 kilograms. It falls a distance of 10 meters, and it falls from velocity of 0 to velocity of 12. So we want to see which of the following correctly identifies if the system is open or closed, or it describes the net external force. So right off the bat, I know that a closed system has to mean that the net external force is 0. And the open system has to mean that the next external force is non-zero. So right off the bat, B and C gone. So now I have to figure out if the system is open or closed. The way that I could do that is that I'm going to calculate the energies from beginning to end. So initially, this object has potential energy because it's from a distance from the ground. So U, and then by the time it reaches the ground, all that potential energy will turn into kinetic energy. So U equals mgh, kinetic energy equals 1/2 mv squared. So I'm going to plug in what we're given. So 5 times 10 times 10, which is 500 joules. Kinetic energy, we got 1/2 of mass, which is 5, velocity squared, which is 12 squared. Let's see how much that is. I think that's 380 joules, but I already know that these don't add up to each other. Also, if this is not 380, you can correct me if I'm wrong, but I already know that they're not going to equal each other because some of that mechanical energy got turned into thermal energy due to air resistance. Okay, so due to air resistance, that energy that should have been 500 lowered down to 380 because air resistance turned that mechanical energy into non-mechanical energy. Wow. So the net external force is going to be non-zero. So this just means there is going to be external forces. And then we know our system is open. All right, letter B. So a toy car has an initial acceleration of 2 meters per second squared. So acceleration is 2 meters per second squared. I have my little picture here. It's released from rest. It goes from a velocity of 0 to velocity of 25 meters per second. Is the car an open or closed system, and why? So the ways that I could figure this out. I could use my conservation of energy equation. E initial equals E final. So I can figure out what are my energies in the beginning. In the beginning, there's not really potential energy because it's on the ground. There's not really kinetic energy because it's not moving at all. So I can say initial energy is 0. Final energy, it's moving, so there's kinetic energy. So right off the bat, I already know that if I wanted to fill in numbers for these, then I could say that, I'm just going to bring it over here, 0 equals 1/2 mv squared, so 1/2 of whatever the toy car is, which replace the mass with 1, velocity is 25 squared, and 0. So if I were to fill in these numbers, I can see that they actually don't equal each other. So my energy, my total mechanical energy in the final is going to be greater than it is in the initial position. So that means an external force had to have been applied to the system, causing it to be open, and that is letter B. So open because external force was applied, which is causing the car to accelerate. So this external force could have been someone pushing it. Okay, so this little dude just pushing the cart, causing it to accelerate, and therefore there is a external force causing it to be open. Wow, that was very repetitive. Next question. All right, going on to number 9. Number 9 is a perfect example of a very lengthy question that kind of throws you off, but if you know certain things, then you can answer it pretty quickly. So a student performed an experiment where the ball is going to be traveling in a perfect circle horizontally. So it's like if I was holding a lasso. I don't really know how to lasso, but it's just a horizontal circle. We know that the system is going to contain the ball, string, and student. Okay. We want to know if it's open or closed. Well, it didn't include Earth. Because it didn't include Earth, then we have to take into account force of gravity. Okay, force of gravity. So that immediately is going to be an external force that is being applied onto the system. So immediately it's going to be open. We can mark out C and D. Letter A says an open system because a net centripetal force of tension is exerted on the ball that changes the direction of the ball. Well, the centripetal force is actually included in our system anyways. And again, the centripetal force is going to be due to the tension of the string, which is included in the system. The graph kind of throws you off. It just verifies that the tension is constant the whole time. All right, number 10. So number 10 asks us about the kinetic energy, which position has the greatest kinetic energy. And we want to figure that out using free body diagrams. So if we're looking at free body diagrams, we're going to notice that these free body diagrams are predominantly different in that we have friction and the spring. So as we can see here, whenever it's compressed, there's very little force of friction, but there's more force of the spring. In the middle, the forces are kind of even, and up here, friction is kind of pulling it back. So let's start with the last one. So because friction is pulling it back, this block, its velocity will be approaching 0. And that's going to be the same thing with x2. So because, although it's not friction that is pulling it, it's going to be the force of the spring that is pushing it and providing it an acceleration. However, because it has the acceleration, it doesn't necessarily mean it has that velocity yet. But in the middle, this is when the block is in full swing. It's in full, it has all of its velocity, and it's just traveling at a nice constant velocity. And these forces are equal to each other, which tells me that acceleration would be 0, and then there is a constant velocity. So then my answer would be Y. So number 11 is talking about the change in kinetic energy. And I know my kinetic energy equation, which is 1/2 mv squared. Just the problem is that it includes this little bump in the road where there's friction randomly over here. So how am I going to find the change in kinetic energy when I have to take into account this little frictionless surface in 2 meters? So what I can use is my work energy theorem. So where work equals change in energy. So change in energy would be equal to change in kinetic energy and change in potential energy. My bad, that's U. We know that there is no change in potential energy because this block is just moving side to side. So then in total, it would be my work equals kinetic energy theorem. So that's what I'm going to have to use. My work of what, right? So we know that if there is an external force on the object, so this object is moving to the right, but we know that whenever it reaches that path, there is going to be a force of friction being applied to the block. Okay, so there is a force of friction that is being applied to the block, and it's going to be opposite to the direction of motion. So I already know that it's going to be a negative work of friction. Okay, so the work due to friction equally to kinetic energy. Work is going to be equal to force of friction times distance. And then I'm going to expand that equation with my force of friction, where force of friction is mu times force of normal times distance. And then my force normal, because there is no movement in the up or down direction, force normal, we can just use our force of gravity in place of force normal, because Fn equals Fg, because F of n, F of g, there's no movement in the up or down direction, so forces are equal to each other. So we have F of g over here, and then I already know that F of g is going to be mg, so I'm just going to elaborate mg over here times distance, and now I'm going to plug in everything. We have 0.2 for coefficient of friction, mass is 5 kilograms, gravity, let's do 10, distance, it's going to be 2 meters. And then once I plug all those in, I can find the change in kinetic energy. And that's going to be 20. So it's going to be negative 20 joules. So that means that 20 joules is going to be removed from the block, and that's going to be A. Notice I did not use 10 meters per second at all, and that's just the perk of using the work energy theorem. So again, this is called the work energy theorem, and you just don't have to use velocity in this equation. Alright, so we have this object in projectile motion at point P and Q. So at point P, I do have some potential energy and kinetic energy. Q, I have potential energy and kinetic energy. My ground, H equals 0, height equals 0, is going to be on the bottom. So therefore, I'm going to state that there's potential and kinetic energy in both situations. I want to describe the total energy of the system for points Q and P, and that's why it's going to be C. Some people will choose B because they think that at point P, where it is at like the top of its path in projectile motion, they'll think that, oh, velocity equals 0. But no, velocity in the y direction equals 0, right? Velocity in the x direction, however, is going to be non-zero. So therefore, there is kinetic energy, like we have here in point P. And in point Q, of course, there's potential and kinetic. Next question. 13 is kind of a doozy in terms of calculations, but if you have the calculations down, then you don't have to do it, you can just do it theoretically. So a ball of mass m is attached to a string, negligible mass. We want to find at what point does the ball, string, or system move, what is true about whenever it moves from point 1 to 2. So potential energy decreases, and the tension of the string increases. So we know for sure potential energy decreases and tension increases. We just need to know by how much. So let's start with potential energy. So with potential energy, I know that whenever I get from 1 to 2, I know that U will equal mgh. So U at 1, we have mass, gravity, and some sort of height. What is this going to be? So this height is going to be 2r, because the radius multiplied by 2 is going to be the height of 1. The potential energy of 2 is going to be mg0, because my height is going to equal 0 down here. Right? So that means my potential energy going from 1 to 2, where 2 is going to be 0, I know my potential energy decreases to 0 by mg2r, so at least I can X out A and B. Tension of the energy increases by 2 mg or more than 2 mg. How do we figure that out, right? So if we wanted to figure out tension of the string, well, I know that the ball is traveling in a centripetal motion. So if it's traveling in centripetal motion, then this tension is going to be equal to my centripetal force. Okay, so it's equal to my centripetal force, but there's also gravity playing a part in here. So at 1, there's tension of the string, but there's also gravity pulling down, so force of gravity. So if we know that centripetal force will equal my sum of all forces in the centripetal direction, so force of gravity plus tension, I know that we know that centripetal force is going to be equal to my mass times v squared over r equal to force of gravity, which is mg, plus tension. And if I wanted to find tension, then all I need to do is that the tension at point 1 is going to be, so T of 1 is going to be mv squared over r minus mg. So the tension at 2, that's going to be the exact opposite. It's going to be mv squared over r plus mg. Okay, so the reason being is because we have force of gravity, F of G, over here, and then tension up here. So this direction, tension is going towards the center of the circle, so that means it's going to be positive. Force of gravity is away from the center of the circle, so it's going to be negative. So because it's negative, that sign just changes. And now we have to figure out, how does tension increase, going from 1 to 2. So let's figure that out using, we can use velocity. So in order to find the velocity, we're going to use our conservation of energy equation. So energy 1 equals energy 2, or 1/2 of mv squared plus potential energy, which is mgh, is going to be equal to just 1/2 mv squared. My masses cancel out, so it's 1/2 v squared plus g times the height, which is 2r, as we stated before, equals 1/2 mv squared. If we solve for the velocity at t2, so let's just solve for the velocity at t2. So t2 is going to be my final position, right? So this is going to be 2, this is going to be 1. I'm going to get v at position 2 is going to be the square root, just skipping a few steps, square root of v velocity at 1 squared plus 4gr, so just skipping a few steps. So if you plug all this into this part right over here, then you're going to get a meow. You're going to get T2 equals, mv squared 1, so for velocity at position 1, r, plus 5 mg. So that's a lot. So the tension at point 2 is going to be a lot more than at position 1, so therefore it's going to be increasing by more than 2 mg. So mainly what you have to do with this problem is that you have to just know your equations. So at point 1 we have a lot of potential energy. Point 3 we have potential and kinetic. At point 2 we also have potential and kinetic. So for letter C, it says that the mechanical energy of the system at point 3 is less than at 1. So we're just going to plug in the numbers for the equations that they give us. So let's calculate first point 3. So mechanical energy. So the energy at point 3 is going to be potential plus kinetic. That's going to be mgh plus 1/2 mv squared. So then we have a mass of 0.1 times gravity times height, which is going to be 2r. So it's 2r because radius plus radius will be 2r. So it's going to be 2 times 0.6 meters plus 1/2 of 0.1 v squared, which is going to be 2.5 meters per second. 2.5 meters per second, okay, squared. And then for the energies at 1, we have potential energy, which is going to be mgh, and that's going to be 0.1 times 10 times height. So the height at 1 is going to be 1.8 meters. Whenever you calculate that out, you have at point 3 it's going to be 1.5. So at 1 it's going to be 1.8 joules. Whenever you calculate that out, at 3 it's going to be 1.5 joules. So we got some mechanical energy being lost here. So this is going to be side note open system, and that mechanical energy gets converted into non-mechanical energy. Let's move on to the next question. So the next question, we got a nice little Atwood's machine. So this Atwood's machine asks you to look at the center of mass. So we know that the center of mass is going to be closer to the heavier objects. So if it's closer to the heavier objects, then we know the center of mass is going to be right over here. So since object Y is going to be moving down, we know that the center of mass will be moving to just right about here after the object Y falls. So the direction of motion, so D, is going to be going from blue to red. So we also know that we need to figure out if gravitational force will do positive or negative work. So this is going to be my answer choices. So we need to figure out if gravitational force does positive or negative work. We also need to figure out if kinetic energy increases or decreases. Well, we already know that kinetic energy will increase because the object starts from rest and then it increases in speed. So we can just mark out C and D. Gravitational force is going to do positive work. So it's going to be A. The reason why it does positive work is because the work is going to be in the same direction as the direction of motion. So we know that gravity is going to be pulling down, so force of gravity. So force of gravity is going to be same direction. The angle between the two parts is going to be 0, and therefore it's going to be A. Moving on to the last question. Woohoo! If you have taken the time to watch this entire video, I want to say thank you for watching this video and putting in your work and hard labor for physics. I'm sure your work will be paid off. And thank you for listening to my amazing voice at 12:35 a.m. Good God, it's 12:35. So yay, last question. All right. So this object is launched from a surface. So if it's launched from a surface, it's going to have some sort of potential energy and also spring potential energy, and then it's going to travel down and it's going to turn into kinetic energy. We know that we want to find the distance from the base of the table as affected by the mass of the objects. So if we look at the mass of the object, so K equals 1/2 mv squared. So what if we did K equals 1/2 of m over 2 velocity squared. So I know that all this potential energy will turn into kinetic energy. So 1/4. So I know that if I were to calculate for velocity, then I know that my mass, I'm going to replace that with 1. It's just an arbitrary 1. And I'm going to solve for velocity. Velocity will end up being 2 meters per second. So velocity is equal to distance over time. Time, I'm also going to replace it with 1. So velocity is 2 equaling to distance. So this is going to be the ball with half mass. And then we can do the original ball. So original ball. So K equals 1/2 mv squared. So I'm going to replace K with 1, M with 1. So it's 1/2 v squared. And then v is going to be equal to the square root of 2. So then the square root of 2 is going to be equal to distance. So if we take a step back, compared to the original ball, which has a mass of m, and then the mass of half the mass, we can see that the distance between that these balls will reach will vary. So the ball of lower mass will reach a larger distance, up to 2d, so 2 times the distance, and the ball of a larger mass will have a square root of 2. So square root of 2 is going to be about 1.4. So this is about 1.4. So if we look at our answer choices, I can see that my answer is going to be greater than D, which is 1, but less than 2D, which is 2. So 1.4, 2, 2, it's going to be C.